Okay, so let's just figure out the relationship between the angular quantities versus linear quantities, or sometimes you'll hear the word tangential quantities. So for example, on our circle, we've already talked about this a little bit. We have our angle theta, we have our radius, we have this distance right here, which is what we call our S here. That's would be kind of our linear quantity. This would be the distance that we travel here, right? We physically actually travel that distance. So actually, let me just do this visually for you so you can see this. So if I have our wheel here, and if we rotate our wheel around like this, so things are going to change, and things are going to be the same. But if we have something right here, and it's traveling around the wheel, okay, in a second, it's going to traverse the same angle, regardless of whether I'm on the edge here or whether I'm close to the center. So like in a second, let's say it moves from here to here, it's going to travel the same angle regardless if I'm close or if I'm far away. So the angular quantity is the same for both. Both the angle or the angular speed would be the same, or even the angular acceleration. However, the linear quantities, and by linear or tangential I mean at this point, this has a very specific speed that it's moving this way. Like if I were to let it continue in a straight line or tangent to the circle, it would continue at some speed, right? And so that's what we refer to as the linear or tangential quantities. Well, your linear or tangential speed is going to change depending if I'm far away or if I'm close. In which case are we going to be moving faster? If we're close to the center or far from the center? Okay, far from the center, right? And the reason for this, if you think about it, in one revolution, regardless of where I am, what's true about the time it takes to go in a circle? It's the same, right? Regardless. However, in which case am I traveling farther? The farther we are, right? Because here I have to travel a large circumference, whereas where I'm close, I'm traveling a smaller circumference. So you're traveling a farther distance in the same period of time. So you have to be going faster when you're on the outer edge. All right? So anyway, that's what we mean about angular versus linear. So you have a certain angular velocity, which would be your radians per second. Your linear is going to be meters per second, as we would talk about. So we've already talked about the relationship a little bit. We said that S was equal to r theta. And remember, S is just a distance. So I could just as easily call this d equals r theta. They just use the term S. I could also call it, say, delta d, and delta d would be equal to r delta theta if we're talking about a change. Okay? So this is one relationship here. We could also write this as, well, let's see what the velocity is going to be. Our basic equation for velocity is delta d over t. Right? Well, what if I make this substitution here and I get r delta theta over t? But what if I just group this differently? What is delta theta over t called? Angular velocity. Right, so we could also write this as r omega. So notice that S equals r theta and V equals r omega. Or I'll put it over here so I can box it nice. So V equals r times omega. Well, let's look at the acceleration. We know acceleration is delta V over t. Okay, well, delta V we just said was r omega. So delta V would be r delta omega. Okay, well, let's just group this differently. And what is delta omega over t? Angular acceleration, right? So we could write that as r alpha equals a. So notice the relationship between angular and linear is very straightforward, right? All you're going to do is multiply by the radius. So to find the velocity, you would multiply the radius times the angular velocity, and so forth. Okay? So that's pretty straightforward. Well, let's then go to our kinematics equations. Let's take the first one, and I know I showed this to you in the warm-up, but let's formally derive it. So we know Vf equals V naught plus At. Well, let's just go ahead and make the substitutions up here for this and this. So we could write this as R omega final equals R omega initial plus R alpha time. Well, I have r's in all three terms, right? So what can we do? Cancel those out. And so what we're left with is omega final equals omega initial plus alpha t. Notice that it's identical except, we're just different things. So this is omega instead of v, this is alpha instead of a. Okay? And I'm not going to do it, but we can do the same thing with all four kinematics equations. So let's just go ahead and write them down. So number 2, we have our delta D equation, right? What's delta D? What's the equivalent to delta D? So is it R or is it S, R, or theta? Theta, yeah, it's theta. So we're going to write this as delta theta equals 1/2 omega final plus omega initial times t. Okay? Number 3, delta theta equals omega initial t plus 1/2 alpha t squared. Omega final squared, omega initial squared plus 2 alpha delta theta. Okay, here's our 4 angular kinematic equations. Okay, so let's do an example here.